Our world runs on these incredibly complex systems. I mean, think about the electricity powering your screen right now, or the weather patterns that decide if you need a jacket. They're all this chaotic dance of countless moving parts. But what happens when they get so complex, so tangled, that we can't predict or control them anymore? Well, let's dive in and find out.
It kind of sounds like the start of a riddle, right? What do our power grid and the weather actually have in common? Well, they're both these massive, sprawling, unruly systems that are getting almost impossible to fully grasp in real time. But there's a really powerful idea, a shared way of thinking that's helping us finally tame them.
So here's our game plan. We're going to explore this art of simplification. We'll kick things off with the core problem of complexity, then introduce the really elegant solution. After that, we'll look at two pretty fascinating case studies, one on taming the modern power grid and another on decoding the flow of fluids. And finally, we'll zoom out to see the bigger picture. Okay, so let's get right to it. What's the fundamental challenge here? Why are these systems suddenly becoming so difficult to manage?
So here's the crazy thing. The problem, believe it or not, is that our models have gotten too good. We can now create these simulations for power grids or weather that are just unbelievably detailed, with millions and millions of variables. But that amazing detail comes with a huge price. They are so computationally heavy that they just become intractable. We can't get the answers fast enough for them to be of any real use.
Now there's a technical name for this specific problem, and it's called stiffness. A system gets stiff when you have things happening on totally different timescales all at once. So in a power grid, for example, you've got these little electronic inverters reacting in microseconds, while at the same time, the huge mechanical turbines in a generator might take several seconds or even minutes to respond.
And I love this analogy, because it just clicks. Think about it. To capture the blur of a hummingbird's wings, you need a ridiculously fast shutter speed. But if you use that speed, the turtle looks like it's completely frozen, not moving at all. To solve this with a computer, you have to take these microscopically tiny time steps, and that just makes the entire simulation grind to a painful halt.
Okay, so if the full super detailed picture is just too slow to be useful, what's the solution? Well, we have to find a simpler view. We have to find the essence. This is where a really powerful technique called model order reduction, or MOR for short, comes into play. The best way to think about it is like the difference between a satellite image of a city and a subway map. The satellite photo has all the data, every street, every building, but the subway map, it throws most of that away to show you only what's essential, how to get from point A to point B. That right there is the art of MOR. So conceptually, you can break it down into three basic steps. First, you take a look at the entire, messy, complex system. Second, you figure out what the most important parts are, the slow, dominant behaviors that really define how the whole thing works. And third, you build a brand new, much simpler model that only has those essential dynamics, and you just toss out all the fast, noisy, complicated details.
And really, it all comes down to this trade-off right here. The full model, it has everything, but it's just too slow. The reduced model, on the other hand, it's not a perfect carbon copy, no, but it beautifully captures the key behaviors you actually care about. And, this is the important part, it runs fast enough to be used for real-time control and prediction.
Okay, so that's the theory. Sounds pretty neat, right? But how does this actually work in the real world? Let's take a look at our first case study, which comes from some incredible research at ETH Zurich on our increasingly complex power grid.
The challenge we're facing right now is that as we add more renewables like solar and wind, the whole nature of the grid is changing. See, these sources connect through electronic inverters, and those things operate on millisecond timescales. This makes the entire grid way faster, more dynamic, and, you guessed it, a whole lot more stiff and way harder to control.
What the team at ETH did was just brilliant. They came up with a new approach that goes right after this stiffness problem. They used this clever mathematical trick that basically, it rotates their point of view on the system. And this new perspective neatly separates the super fast, headache-inducing dynamics from the slow, important ones. Once they're separated, they can just chop off the fast parts, leaving them with a much simpler model that, amazingly, still has the same crucial stability as the original.
And the payoff? Get this. Their simplified model allows for a computational speedup of up to 100 times. 100! That's the difference between a simulation taking over an hour versus taking less than a minute. For someone trying to manage a power grid, that is an absolute game changer.
All right, so that's the power grid. A huge deal. But this same exact challenge pops up in a totally different world. Fluid dynamics. Think weather forecasting or even designing a better airplane. Yeah, anytime you're trying to predict a hurricane or design a more aerodynamic car, you're wrestling with fluid dynamics. And the simulations for these things, they can have literally millions of variables, describing the velocity and pressure at every single point in a 3D space. It's the very definition of computationally intractable.
So for a long time, researchers were kind of stuck between a rock and a hard place. On one side, you had a method called POD. It's computationally cheap, which is great, but it can be super unpredictable. Sometimes the simple model it creates is just wrong or even unstable. On the other side, you have balanced truncation. It's super accurate, really robust, but it's so computationally demanding that it's basically impossible to use for the giant systems we see in fluid dynamics.
So, what do? Well, researchers at Princeton came up with this genius hybrid method they call balanced POD. It's so clever because it combines the absolute best of both worlds. It takes the low computational cost from POD and marries it with the incredible accuracy and robustness that makes balanced truncation so powerful.
And you can see just how well it works right here. The numbers really speak for themselves. In their tests, the old pod method had about 10 times more error than their new balanced pod method. But, and this is the kicker, balanced pod kept the computational cost just as low. You're getting near-perfect accuracy for a bargain price. It's incredible!
Okay, so we've looked at power grids, and we've looked at fluid flows. Let's zoom out for a second and think about what this all really means.
Because what we're really talking about here isn't just a couple of neat tricks for specific problems. Model order reduction is a fundamental principle. It's a foundational way of thinking that lets us understand and even control systems that would otherwise just be completely beyond our grasp.
In this way of thinking, it's not just in one or two niche areas. It is absolutely critical across the board. The research we looked at today pulls from a long history in all sorts of fields. It's essential in control theory, power systems, fluid dynamics, really any area of science and engineering that has to deal with complex, messy, nonlinear systems.
So at the end of the day, this is about more than just making computers run faster. It's a way of thinking. It's about having the wisdom to ignore all the overwhelming noise and instead find that simple, elegant truth that's hidden inside, governing how the whole thing behaves. It's about creating that subway map from the chaos of the satellite image.
And that really leaves us with a huge, fascinating question, doesn't it? Our world, from our economies to our biology, is only getting more connected and more complex. So what's the next big, unruly, seemingly impossible problem that we can finally solve just by learning how to find its simpler view?